Graph transformations. Another way that we can get new functions from old functions is by putting some mathematical operations onto a function which impacts the way it looks and behaves in a graph. So we're going to look at the different things we can do and what sort of impact it has on our function. So the first transformation that we're going to consider is rotation about the x-axis. That means we're going to have a graph and we're going to mirror it around the x-axis, which is the horizontal axis. The way we do this is by multiplying our function by -1. So for example, if we have the function f of x equals x squared as our original function, then the picture of that will look like a parabola, which is a U shape. By multiplying by -1, we get g of x, which equals -x squared. So that negative is what multiplied our function, and that flips our picture around the x-axis, meaning now it looks like a hill instead of a U. The next thing we can do to a graph is multiplying it by a constant that is between 0 and 1. So that means we're going to be multiplying by some fraction, and the result of that is going to be that it's going to shrink our graph. So consider the function f of x equals sine x. So sine x has a picture that looks like this. So sine lives between 0 and 2 pi. And then it goes all the way up to +1 and all the way down to -1. If we were then to multiply that by -1/2, the result will be a graph that only goes up half as high and looks like this. So notice that my new graph goes to the same zeros. Starts at 0, ends at 2 pi, and travels right through pi just like the original did. But now, the maximum height of my graph is half, and the minimum is going to be -1/2. So what happened was every single y value was cut in half, and it still goes to the zeros because half of 0 is 0. If we were to now multiply our function by a constant that is bigger than 1, the result is going to be what's called vertical stretching. So consider now the function cosine of x. Cosine of x looks like this, comes down, comes up, and it also lives between 0 and 2 pi. It's got a maximum value of 1 and a minimum value of -1. If we were to multiply this function by 4, what that's going to do is it's going to stretch all the y values so it goes up 4 times as high and down 4 times as low. And that will look like this. So again, my graph is going to live between 0 and 2 pi, and it's going to cross through zeros at the same spot. But each y value is going to go up 4 times as high as the original or 4 times as low because we're multiplying every single y value by 4. So again, if we multiply by a negative, it'll rotate our function about the x-axis. If we multiply our function by a number that's between 0 and 1, it will shrink our graph by that factor. And if we multiply by a number that's bigger than 1, it will stretch our graph. There are other things that we can do as well. So let's look at the next batch of transformations. The next types of transformations that we consider are shifts. So we're going to take our graph and we're going to move it around in space. The directions we can move it are up and down or left and right. So we start with a vertical shift. The vertical shift is going to happen when we add or subtract a constant from our function. If we add a constant, that's going to move our graph up. If we subtract a constant, that's going to move our graph down. So here, k is a constant. So consider the function e to the x. E to the x is exponential, and it crosses through at x equals 0, y equals 1. So here, if we were to take this function and we were to add 2, e to the x plus 2, what that would do is it would shift our function up by 2 units. So e to the x plus 2 is the same function shifted up 2 units. If we were to consider what would happen if we subtracted 1, it would take our function and it would shift it down 1 unit. So then we would have e to the x minus 1. So instead of crossing through at 1, it would cross through at 0 because that whole point was moved down 1 unit as well as all of the other points. So this is somewhat intuitive, that if you add a number to your function, it'll get shifted up that many units. And if you subtract a number from your function, it'll get shifted down that many units. The horizontal shift, however, is not as intuitive. Instead, it's a bit counterintuitive. So consider the function x cubed. The function x cubed looks like this. And it turns out that if you were to subtract a number from inside the argument, so notice here we are now inside the argument. If you were to subtract a number in there, that's going to move it right k units. So subtraction moves your function right. Now to me that's counterintuitive because if I subtract something, I really want to move it to the left, but that's not the case here. And if you were to add a number inside the argument, that's actually going to shift it left k units. So going back to our x cubed, if we have x minus 4 cubed, that's inside the argument. And since subtraction, it's going to move right 4 units. 1, 2, 3, 4. So now it's going to have the same shape, but it's going to cross through at x equals 4. Now, if you were to plug a 4 into that function, you would get 4 minus 4 cubed, which is 0. And that's what we want. When x equals 4, y should equal 0 because that's where we cross through the axis. Similarly, if we consider x plus 1, that means we're shifting left 1 unit. So here we're going to come down and we're going to go through at negative 1. So again, even though it's counterintuitive, if you subtract, we move right. And if you add, we move left. Now for all of these actions we can take on a function to shift around the graph or to move it around, we can take multiple. So we could move a graph up and right and rotate it and stretch it if we wanted to. So now that we know what these actions do, let's look at some examples of how we can use these to figure out the way that graphs are changing. Example 1. For each of the following situations, we're going to write a formula for the resulting function, and we're going to graph the original and new resulting function on the same axes so we can see what kind of impact it's had. So our original function is x cubed. So I'm going to go ahead and I'm going to draw that. X cubed roughly looks like this. And again, if you don't know what a graph looks like, feel free to graph it on your graphing calculator. Now what we want to do is we want to shift it up 4 units. So if we're going up 4 units, we're going to add plus 4 to our function. We're going to stretch it by a factor of 4. So we're going to multiply our function by 4. And we're going to shift it left 3 units. So remember, slightly counterintuitive. So that means we need an x plus 3 inside the functional description here. So that means that my g of x, which is my new function based on my f of x, is going to be 4 times x plus 3 cubed plus 4. So So the 4 out front stretches it by a factor of 4. The plus 3 in the argument is what's going to shift it left 3 units. And the plus 4 at the end is what's going to move it up. So since I'm going to go up 4 units, 1, 2, 3, 4, I can think about what happens to this 0, 0 point. And then I'm going to go left 3 units, 1, 2, 3. So in space, I'm going to come on over here. And then I'm stretching it by 4 units, which means it's going to go up a little bit faster than it was before. So it's a little bit quicker on either side. And my new function looks a little bit like that. So again, I shifted it up 4, left 3, and I stretched it by a factor of 4, which means it's going up and down much more rapidly than it was originally. For the second one in this group, we're starting with the function f of x equals the square root of x. That's our original function. We want to shift it right 3 units. So that means inside the argument, we need an x minus 3 and up 2 units. So a plus 2. So we start with the typical graph of the square root of x. Looks like that. Starts at 0. And now, if we shift it right 3 units and up 2 units, 1, 2, 3, 1, 2, that means my new graph is going to look like that. It's going to look the same, but it's starting at a new point, right? So it's going in the upward direction, and it's bending towards the top. This function, the formula for that is going to be the square root of x minus 3 plus 2 is what our new function is. The x minus 3 gets plugged in wherever we saw an x in the original, and then the plus 2 is what shifts it up. Let's try one more. So finally, we're considering the function e to the x. So again, the original function is e to the x. E to the x looks roughly like that, crosses through at 0, 1. And now we're going to shrink it by a factor of half. So we're multiplying by 1/2. And we're going to shift it left 2 units. So again, counterintuitive, we're going to have x plus 2. So our new function, g of x, is going to be 1/2 e to the x plus 2. So even though the 1/2 is going to shrink everything by half, so things are only going up half as high as we sort of go through what's happening here, the shifting left 2 units is going to cause our graph to cross through at a higher point. So this graph actually ends up looking like this. And you can check that on your calculator. If you graph both e to the x and 1/2 e to the x plus 2, you can see how that all looks. So now we've taken the time to look at how we can graph both of these simultaneously and how we can represent the new function formulaically. Let's look at the next example where we'll study a graph and see if we can determine the transformations that were put upon it. Example 2. Suppose y equals f of x is the graph of the solid semicircle below, and y equals g of x is the graph of the dashed ellipse. We want to write a functional representation that describes the relationship between f of x and g of x. So f of x here lives between 0 and 4. That's the height here. Notice that g of x lives between 0 and -2. I think intuitively we can all see that the f of x, or the blue circle, has been rotated around the x-axis since the red graph lives below the x-axis, which means we needed to multiply f of x by -1 to rotate. However, If we had just rotated it, it would go all the way down to -4. It would be a direct rotation. So instead of going to +4, it would go to -4. But instead, it only goes down to -2. So that means that the y values are being cut in half. Therefore, we need to make sure we're multiplying by half to shrink this graph. So that means that g of x, or the red dotted function, is going to equal -1/2 f of x. So that's a way that we can represent these functions and the relationship between them. The other thing we could have done is we could have talked about what happened to g of x to get to f of x. So we still have that rotation. We have to rotate it no matter which one we're talking about. But if we're going and we're starting with g of x and we're trying to get to f of x, we would need to multiply everything by 2. So f of x is -2 times g of x. Either one of these relationships will describe perfectly what's happening between these two functions. For example 3, we want to use the words that describe how these functions were transformed to obtain the new function. So for the first one, number 1, we have f of x equals x to the 4th, and g of x equals -x minus 2 all to the 4th. So what we can see has happened here is that we've multiplied by a negative in front, which is going to rotate the graph about the x-axis. And additionally, we are inside the function subtracting 2. Remember, if you subtract 2 inside the function, it's going to move it right 2 units. So here, our transformation from f to g is that we rotate about the axis, and then we move right 2 units. Number 2, f of x equals sine x, and g of x equals sine of x plus 3 plus 3. So inside the function, we have an x plus 3. If you add inside the function, that's going to move it left. So this is moving it left 3 units. When you add on the outside of the function, that's what moves it up and down. Since we're adding 3, we're moving up 3 units. So the transformation here is that sine has been shifted left 3 units and up 3 units. For the third one, again, we see that we have this negative out front, so we're going to rotate it about the x-axis. And then up here, we can see that inside the function, we had an x minus 1. So again, if you're inside the function, so you're inside where the x values are going to go, that's going to move left and right. Because we're subtracting, that means we're moving right 1 unit. So here, e to the x has been rotated about the x-axis and then moved right 1 unit. So here we can describe the relationships between two functions because they were related, and we could see the transformations that had happened between them. Finally, we want to be able to look at a picture and a transform picture and make a good educated guess about what transformations have taken place. So consider the graph below, the f of x, that's your original function. And then we have 2 cases of it being transformed, and we're trying to figure out what happened to transform this picture. So for the first transformation, we're looking at the graph directly below. In order to figure out what's happening, it's a good idea to fixate on one point to start to see if that can give you an idea of how it's been moved. So I'm starting with the point 0, 0 at the origin, and I can see that's sort of at the crest of my W. So if I mark the corresponding point on the new graph, I can figure out how that point has moved. So instead of being at 0, 0, it's now at the point 2, 1, which means that my point has moved right 2 units and up 1 unit. Now, that doesn't necessarily tell me if it's been stretched. So I want to check a second point to see if it just moved or if maybe there's some stretching or shrinking happening as well. So I'm going to pick another point, so the right bottom point, and I'm going to see if that point also moved right 2 units and up 1 unit. So before, it was a tiny tad to the right of 1. So by moving right 2 units, that would put it a tiny tad to the right of 3. Well, that checks out. And then it moved up 1 unit. So here, it was a little bit below 2. So that means if I go up 1 unit, it would be a little bit below 1, which it is. So it looks like this is a direct translation where I've moved right 2 units and up 1 unit. So the way I can represent that is f of x minus 2, all of that, plus 1. So inside the argument goes left and right. If I'm moving right, I have to subtract. And then outside the function, if you add something on at the end, that's what moves it up. So that's what happened between my original and this first transformation. Let's look at another one. So again, same original picture, and I'm going to do the same thing. I'm going to fixate on a point and see if I can figure out what happened going from the original to the new function. So here, I notice that my original function has a W shape, but my new function has an M shape. So I'm feeling pretty confident that this graph got rotated. So if I rotate the graph, that means I had to multiply everything by -1. But I'm also wondering if it got shifted. So the way I consider this is to consider a point. If there's a direct rotation, then the maximums and minimums stay at roughly the same point, but on the opposite side of the x-axis. So for example, if I had a maximum at 2, then if I rotate it, I would have my minimum at -2. So here, I have a maximum at 0, right? 0, 0 here. But then, when it's rotated, I now have a minimum at 1. So it's not still at 0. If this had been a direct rotation, it would have stayed at 0. So something else has happened. Let's look at some of the other points here. So this point here and here, down at the bottom, these minimums, these are about -2.1, -2.2, somewhere around there. But notice that if I had just rotated this, that's where these maximums would be. But these maximums on this new function go up a little bit above 3. So since they weren't a little bit past 2 and instead were a little bit past 3, I have the thought that I think this was shifted up by 1. So I think about this 0, 0 point. If I rotate the graph and then I shift it up by 1, that would move if I rotate this graph and then shift up by 1, that would match where this maximum turned into this minimum. Because when I rotated it, it would have been at 0, but by shifting it up by 1, that's what got it to be in the right place. And the other points match that as well. So I'm going to go up 1. So this new function, I can write as -f of x plus 1. So I've rotated it and I shifted it up 1.